Hey, hey, this is amazing. I've been doing machine learning infrastructure for a long time. I was just looking at the venue when I came here, and I remember that in 2008, I participated the NeurIPS conference. They organized a small workshop called Open Source for Machine Learning. It was this small basement with 40 people. And like most people there were just authors of packages, no users back in the day. So this is nice, right? This is a very nice venue. So I'm super excited today to talk about more data science with less engineering. I'm really passionate about this topic and how we do this at Netflix. But the main reason why I'm really excited about to be here today is the fact that like now, all the stuff that I will be talking about is actually available for you right away. So always before, when I've been talking about how we increase data scientist productivity at Netflix, it has been a bit hand-wavy and theoretical in the sense that like the tools that we have internally available at Netflix haven't been open source. But now, on Tuesday here at re:Invent, we finally open sourced Metaflow. So all the stuff that I will be talking about today will be available for you like right away at metaflow.org. But I hope that you will stay here instead of just like starting to pip install stuff. But today we will be talking about Metaflow and how we increase data scientist productivity. But let me start like with some motivation. So why we are doing this thing in the first place, why this is important. And I do believe that like things I will be saying hopefully are not only relevant for Netflix, but also for your organizations. So here's a data scientist. And let me ask you, how many of you work with data scientists overall? Okay, good number of people. So I hope that these ideas resonate with you. So here's the data scientist, and now the question is that why do your companies hire data scientists? Hopefully it's not just because ML and AI is really hyped and cool. There must be some business reason. And the reason like why Netflix hires data scientists is that data scientists solve really hard business problems that would be nearly impossible to solve without data science, without machine learning, and without having large amounts of data. And now the next question I want to ask you is that when you have a business problem and you have a data scientist there in the middle, how do data scientists do data science? Like, what does it actually mean? Like when you, let's say you are the business stakeholder, you go to the data scientist and you ask them to solve this important business problem, lifetime valuation, maybe marketing, something like that. How do you do it? Well, maybe there's a small data set that you can start with. You can share it with the data scientist. And what the data scientist typically does is that they can open a Jupyter notebook on their laptop. And it's easy enough. You take the CSV, you like load it in pandas, you start hacking something in a Jupyter notebook. And life is pretty easy. Maybe you look at the distribution, you start exploring the data and like forming a mindset about the problem. So that's a good way to get started with data science. And what's really exciting today, and what's the big difference to that open source machine learning workshop back in 2008, is that there are absolutely amazing open source libraries available for doing machine learning. Things like TensorFlow, things like PyTorch, things like Keras, things like XGBoost, scikit-learn, all those things. And it's mind-blowing amount of resources that companies put in making these libraries high performance and relatively highly usable and so forth. So you can take the off-the-shelf library, you can use it in a notebook, life is easy, there's really no problems with that. Now, you keep prototyping in a notebook, and eventually you get to the point that you know that, okay, so it seems to work, I have an idea how to make it work with this small CSV. But the next step I want to do is that I want to access more data, maybe from a data warehouse, and like maybe just start getting a bit more realistic idea what's going on. And also, I know that as a data scientist, I should be a bit more disciplined than just having notebook 1, notebook 2, notebook 3 on my laptop. Maybe I should start versioning my code. Maybe I should even start versioning my models, maybe versioning my data. So, and that requires some thinking there how to do it well. Now, when it comes to the data question, oftentimes the challenge, and this is a challenge that we oftentimes see at Netflix, I'm sure that many of you see as well, is the question that maybe the data isn't readily available, but you actually need to run some kind of an ETL to get the data set you need. And maybe here the data scientist works with the data engineer to get the data set they need. And it's kind of okay. I mean, it's doable, but I mean, it like adds some friction there. But I mean, I hope that the state of the ETL tools would be better, but I mean, there are still like ways to make it happen. Now the next step let's say that like you have got to the point that you have a realistic data set on your notebook, you have built the models using TensorFlow, maybe XGBoost, you name it. And now everything looks good enough that you think that, okay, we should actually start testing this in some kind of like a realistic setup. Not quite in production, but at least like start updating the models daily. So what does it mean? Well, everybody knows that you are not supposed to run these production pipelines on your laptop. You are supposed to run these things in the cloud, maybe on your own servers. And this is a big leap. How do you go from this notebook to this cloud environment? What does it mean in practice? Well, now many of these cloud environments these days, they run containers. So you have a Docker container that like you somehow run there. And the question is that where does the Docker container come from? Who builds the image? Is it the data scientist who writes the Docker file, who maybe is able to copy the Python script that they had locally to the Docker and like maybe pip install TensorFlow there? Kind of doable. The challenge there, though, is that, well, I mean, next time you bake the Docker image, the question is that you get the same Docker image. Maybe you need to pin the version of TensorFlow so that these images are reproducible. Another question is that are you supposed to create this Docker image on your laptop? Do you run the Docker build on laptop, or do you have some CI/CD system? Many companies have a CI/CD system, so like there's some mechanism how these images get baked. So it's doable, but especially in the data scientist point of view, I mean, it's starting to get a bit more mysterious how all these pieces fit together. But now imagine that you have got to the point that your model updates on a daily basis. So you have the container, maybe it's scheduled to run, and like the model updates with the latest data. And now what you have is that you have a latest model, and you have only a latest model. It doesn't do anything. It really doesn't solve the business problem. You just have a model. In order to actually do something with the model, you somehow have to connect it with the outside systems, with something like outside your machine learning universe. And now in any large organization like Netflix is, there isn't a single way how you benefit from these machine learning models. So at Netflix, we are solving hundreds of different machine learning problems, and there isn't a single way how we deploy these models. Sometimes we just write results to a table. Sometimes it might be another data scientist looking at the results in a notebook. Or sometimes it might be that we deploy them as a microservice on some kind of a microservice platform. And when I say microservice, basically it just means more Docker containers. So, and now there are, of course, like many solutions available how you can deploy these models for real-time inference. There's SageMaker like provides one. There are many startups providing. We have something internally. So it's doable, but I mean, it starts getting more complicated. And especially it relates to the fact that, okay, now you have the microservice backend that provides something for real-time inference. But now factually what you want to do is that you want to power some kind of a, let's say, a real, maybe an internal UI, maybe some kind of a decision-making support dashboard, and which needs to talk to this backend microservices. And what we have seen in practice is that although the school book examples show you that it's only like predict endpoint, and you send the data from the dashboard to the predict endpoint and you get the results. The reality is much more complicated. In practice, the backends that we provide, they need to provide all kinds of metadata for the UI as well, like when was the model updated, and like what are the data points, like what are the fields that it supports, and so forth. So you have to write a whole bunch of these endpoints. And also in order to configure the React app to talk to the backend, there's all kind of nitty-gritty details there. And now you can say that, well, maybe the data scientist works with the full stack engineer to make this happen. In the same way as the data scientists work with the data engineer and machine learning engineer and a DevOps engineer to make this happen. But this is starting to become a bigger project. I mean, now this is something where you have 5 different people involved. What's the next thing that happens after you have the dashboard? Well, someone will look at the dashboard. Your business stakeholders will look at the dashboard. And now there are 2 things that can happen. Option number 1 is that the business stakeholders are really happy with the result. And they say that, well, the results look really promising. Can we just improve the model a bit? Or can we add a slightly different model? Or can we add some another data set here? And the cycle starts from the beginning. Or like the option number 2 is that the business stakeholders say that, well, actually, it doesn't seem that this will go anywhere. So, I mean, let's just kill this project and move on to the next project. We have better things to do. And again, you will start again with another business problem, and the cycle starts again. And now if you look at this picture, this is the kind of the complicated reality that the data scientists have to face. I mean, there are different ways how your organization can solve this problem. Maybe you have multiple people involved, multiple different organizations. But the question that we started asking ourselves at Netflix is that, like, could we provide some kind of a tooling that the data scientists would have enough support so that they could manage the end-to-end pipeline, the whole cycle, by themselves? And the benefit of doing this is that then first you get super fast iterations because you get that business feedback like as soon as possible. Then you can go back to the drawing board and keep iterating quickly. Or like, and then like another big benefit is that there's also accountability. So since there isn't like situation that you can say that, well, it's not my fault, it's the data's fault. I mean, it's the data scientist who owns it with the full freedom and responsibility to operate this whole end-to-end cycle. But now there are many things involved. As I mentioned, like you have to think about the software architecture. How do you write the code for that machine learning pipeline? How do you version your model, your data, your code? How do you access the data from the data warehouse? How do you scale it to your cloud? How do you debug your models when they inevitably fail at some point? Then when you have the next version, when you are on the second cycle or third cycle, how do you deploy your model so that it doesn't interfere with the previous model? You have to have some kind of a deployment strategy there. Like how do you schedule these things, run on a schedule or whenever the data updates upstream? How do you do this real-time inference in such a way that like you can realistically build actual applications around it? Finally, how do you do operations? How do you monitor that it actually works? How do you alert when things don't work? And finally, it's probably not the single data scientist working on this like for years. It might be that at some point there are other people involved. Maybe you want to hand it over to someone else. So it needs to be understandable enough and not the kind of some like a hairball of code. And these are pretty hard questions, and especially it's hard if the data scientist doesn't have enough support. And this is the mindset that we started with for Metaflow, that how can we improve data scientists' productivity when they have to live in the environment where not only they are building the models, but they would need to be responsible for the end-to-end life cycle. Now, what is fundamentally, what is Metaflow? So, and like how are we going about solving this problem? If you look at those things that I mentioned in the previous slide, there are many things, and how we think about this is that we need a stack of infrastructure. As always, when we are dealing with complex problems, we have this stack that we have to deal with. And we think that the three most kind of the lower layers of the stack are the most fundamental pieces. We always need some kind of a place where we put the data. We need a data warehouse. We need some way how we perform computation on the data. And we need some kind of a way how we orchestrate this computation. So those are kind of the three most fundamental layers here. But then becomes the question that like, how do you architect the code? How do you write these units of computation? How do you then version like these like pieces of code that you write? And then like, how do you operate this whole thing? Like what kind of like alerting, what kind of mechanisms do you use there? And then at the very top of the stack, then finally we get to the data scientist kind of a comfort zone that like then we are talking about things like feature engineering and model development and so forth. And when we actually like started talking to data scientists and asking like how they think about things and like how they would feel if they had the full autonomy of operating like the full life cycle. Well, I mean, first, like people are excited. Data scientists are excited for having the opportunity to own the end-to-end pipeline. And especially they are excited about the opportunity that they wouldn't be slowed down by having to deal with multiple stakeholders, but they could deal with all these things by themselves, as long as someone helps them with the infrastructure. And this is really the picture that emerged, that we know that data scientists mostly care about model development, they care about feature engineering, and the deeper down you go in the stack, the less the data scientists care about the results and about the systems that are being used. We actually have maybe two people at Netflix, two data scientists at Netflix who really strongly care about container management systems, but like that's it, like most people don't. And then conversely, it means that like we as an infrastructure team, we have to help them a lot like with the lower layers of the stack, and we can afford being really opinionated about those lower layers. But then correspondingly, the higher up we go in the stack, I mean, the less prescriptive we can be. And this is kind of almost a paradox that my title is machine learning infrastructure, but machine learning is the one thing that we kind of don't care about. Since if we started being prescriptive about machine learning and saying that no, you can't use TensorFlow, or no, you can't use scikit-learn, but here's the thing that you should use instead, I mean, data scientists would revolt. I mean, they wouldn't buy it. So, and those are the things where they can exercise their freedom and like we can be more prescriptive with other things. Now another big realization that we had at Netflix is that when we look at this stack, we actually do have a technical solution for each one of these layers. We have a data warehouse. We have hundreds of petabytes of data in our S3-based data warehouse. We have a container management system that we use at large scale. We have been doing it for a long time. We have an internal job orchestration system, works well. Of course, we know how to develop software. Like on the software engineering side, we are using Git. We know how to do alerting. We know how to do monitoring. We have an internal dashboarding tool and so forth. And we can use off-the-shelf libraries for model development. So technically, all these pieces exist. But using these things together wasn't easy enough. Like navigating this 8-layer stack just simply wasn't easy enough. And the realization that we had is that we don't have to reinvent any of these technical layers. What we have to do is that we have to provide a unified API for data scientists so that they can navigate the whole stack using a single unified API with the mindset that we want to be less prescriptive about the top layers of the stack and more prescriptive with the lower layers, since that's what data scientists want. And the result is indeed that now Metaflow is a human-centric data science library. It's human-centric because they're in that cycle. It's the data scientist in the middle. We want to give them the autonomy and the independence to operate these pipelines. And it's all about them, not about these systems, because the systems exist and we just want to make them easy enough to use. And now the point why I'm here today at reInvent and why we have the first-class support for AWS, besides the fact that Netflix has been using AWS for a long time, is related to the reason that those lower layers of the stack, like the data warehousing, like compute, like orchestrations, are the layers that historically Amazon has done really, really well. And those are the layers where we can totally rely on Amazon. And we at Netflix, we are extremely pragmatic that when we can ask and when we know that Amazon can provide something, it doesn't really make sense oftentimes for us to do it by ourselves. And that's the mindset that we want to rely on AWS when it comes to scalability, and when it comes to this storage backend, we don't have to do it by ourselves. But then maybe when it comes to providing this holistic picture, then we can provide product like Metaflow. Okay, so that's a lot of talk. So I know that this is a technical audience, so let's get more technical now for the rest of the talk. So I mentioned that our data scientists are not software engineers. And what I mean by that is that they are not software engineers in the sense that they would be building highly scalable distributed systems in Scala or Haskell or stuff that software engineers do. But at the same time, they do write code. When they open that notebook, when they open that Jupyter notebook, they write Python code. It is Python code that you put in those cells. So there's nothing wrong. I mean, we have nothing against, data scientists have nothing against writing Python code. But the Python code that they write is a bit different. So it's not like that you have object hierarchies and you really carefully design the architecture. You just get your job done. Maybe you have this function, maybe this is a cell in your notebook where you get some data in, maybe it's a pandas data frame, and you do some processing there, and it's a 7 lines of pandas operations, and then you get some kind of output. And that's type of the code that they write. And now, technically, you could build the whole end-to-end machine learning workflow with this mindset. You could slap 1,000 lines of code in that function, and it kind of maybe works. But everybody knows that kind of starts feeling a bit icky, and having that hairball of a function or hairball of a script doesn't feel right. And early on, before we started with this, I mean, data scientists came to us showing that, oh, here's my script, and this is how I do things. And they came to us saying that, well, I feel that I'm doing something wrong because I don't think that production code should look like this. And they asked that, well, should we start using object orientation? Should we start using modules or packages? And by the way, what's even the difference between modules and packages in Python? And how should we go about it? And we realized that, well, they do need some help with software architecture. They do need some help how they structure their code. At the same time, they shouldn't have to think too much about it. And the abstraction that we chose, as what many others have chosen, which is by design, it's nothing new, is that you can structure your workflow as a directed acyclic graph. And why this is so useful is that this is kind of a very natural way how data scientists would even explain their workflow to you on a whiteboard. They would say that, look, here in the first step, I load my data, and once I have my data, I train 2 different versions of the model. I train the XGBoost model, and then I run a TensorFlow model, and then I choose the one that performs the best, and then I write the results to a table. And that's a workflow. And now we say that you can take that Python code that you have in your 1,000-line function, and you can just organize it a bit as a workflow. And how it works in Metaflow is that you just derive from this flow spec. It's just a class, and every node of the graph becomes this one method decorated with the step decorator. And now the edges of the graph become these self.next transitions. And now if you look carefully, you can see that the code that we have on the right-hand side like fully describes the DAG that we have on the left-hand side. So we have the nodes and we have the transitions. So that's the DAG. That's a DAG. Nothing too special about it, but importantly, it allows you to structure a code a bit. And like some of the more complex workflows we have may have a 20, 30 steps. And like, of course, I mean, they get kind of long, but at least like you have really now some structure in your code. And this might not sound like much. And like, let me actually like show you how it works in practice. So now what you can do today, luckily because it's open source, you can just pip install Metaflow. And it installs the latest version of Metaflow now. And Metaflow comes with this really nice command line interface, colors, everything. It comes with tutorials. So let's just pull like one of the tutorials here. The first one is Hello World. And let's just take a look at what the Hello World looks like. It's just a simple Python file, nothing too complicated about it. If we open the file, I don't know if you can see, hopefully it's not too small. It looks exactly what I had on the previous slide. So just a workflow, like a couple of steps. It prints out something, really like a straightforward there. The nice thing is that although the class by itself doesn't do much, it comes with the built-in command line interface. So you can just execute the Python script. And you get a bunch of things for free. You can inspect your workflow, but especially you can run it. And now when you run it locally, it actually executes the workflow locally. And when you just run Metaflow status, there's actually like kind of piece of information showing that, well, I mean, this got run. And now, this is, of course, like for many of you who have used Python like workflow engines before, like Luigi and Airflow, might not seem like much. Like, well, I mean, it's possible to kind of use like these existing engines to do something like this, especially Airflow does this pretty well. And that is, of course, absolutely true, so there's nothing special about executing workflows. The fact that you can do it quickly on your local machine is actually a nice feature. Not all engines come with that. But there's actually more. There's something more that like really makes Metaflow quite special. And it's mainly related to this. So before starting to work on Metaflow, I was using Luigi. I don't know if anyone of you have used Luigi. It's another workflow scheduler for Python. And like Luigi does exactly the same thing. You can define your steps and like you can then execute the workflow, and Luigi does it very nicely. One thing that Luigi doesn't do though is that it doesn't load and store the state. So what you are supposed to do by yourself is that like every step code starts with a few lines of code that loads the data from a database or maybe from S3. Then you perform the computation, and then you write the results back to S3 or database or like whatever like persistent file storage you have. And you do the same thing in every function. And now it adds some boilerplate. So it would be nice to get rid of that boilerplate, but the boilerplate by itself isn't the problem. The problem, like with having that kind of an explicit mode of persistence, is especially that it forces the user to make a conscious decision what they want to store and what they don't want to store. And then like what we have seen, what happens is that like when we ask the user to choose that, do you want to persist this piece of information? The users are usually quite conservative and they say that, no, I don't need that and I only need my model and those are just intermediate results. And then what happens is that 2 weeks after, when the code runs in production, it fails and you get the stack trace saying that, well, I mean, now the model failed in production, and you try to figure out why it failed. And there's no way that you can figure it out because you don't know the state of the pipeline when it failed. And then you go that, oh my gosh, if only I had stored that piece of information, now I would be able to reason like what was the state of the workflow before it failed, but you didn't. And then it's too late at that point in time. So maybe you can go back and then you add like all those lines to store everything. But what Metaflow does for you is that it persists the full state automatically. It persists everything. So let me kind of walk you through this example. So here, like in start, we do the self.x equals 0. Which means that at the start step, after the start step executes, we actually take that value, we pickle the value, we compress the value, we take a hash of the value, and we push it to S3. So we use S3 as a content address file storage in this case, so we don't store duplicate copies. And now when the step A starts, we load the previous value of x that comes from start, we increment it by 1, and then we store that, okay, now in B, like the value of x is 1, and we do the same, or in A it's 1, and like in B it's 2. And now for the join step, now we get the two values, the kind of the divergent values of x, and we choose the maximum here, and then like x is 2 after that. Okay, so it's pretty nice. So you might think that it's just a performance optimization, kind of like a syntactic sugar, if you will, making that boilerplate go away. But actually, there are like more fundamental reasons why we do this. Well, I mean, the reason number one is definitely that this removes the need for the user to choose what to persist, because we persist everything. And I can assure you, some of you might be thinking that, well, it's just too much data. But thanks to the deduplication, thanks to the compression, thanks to the fact that S3 scales so nicely, it is actually like not that much data at all, I can guarantee you. But the next big benefit that we have is that, like, due to the fact that we are persisting the full state, now every step boundary becomes a checkpoint, which means that, let's say your join step fails, and then you go and you fix your join step. Now, since we have persisted the full state of A and B, we can just resume from the join step, and we don't have to execute the whole thing from the beginning. And now you can imagine that, like, if your start step loads data from your Spark cluster and it takes 40 minutes, it's actually pretty convenient that you don't have to execute the workflow from the beginning every time. So the checkpointing is really a nice feature. But the third feature is actually the most important one. And it's related to the fact that, look, when we persist absolutely everything to S3, we get a full audit trail of everything that's created in these workflows. And not only we store every artifact, but we also have a metadata service, runs as a service in the cloud, backed by RDS, backed by Postgres, where we store the metadata about every single execution. So now afterwards, you can go and you ask that, like, well, what was the latest run of my workflow, and like, what are the tags that are related? We also organized everything by namespace, so things are neatly organized. I can ask that what's work that I have done, what's work that my colleague has done, and so forth. And one thing that I didn't mention, like, is that in addition to the data artifacts, we also persist code. So we persist the code, we persist the data artifacts, and I will mention later that we also persist the dependencies. So we kind of have the holy trinity of code, data, and dependencies, which allows you to get this kind of a closure of the full state that allows you to reproduce this machine learning step afterwards, which is really, really useful. But this is not only about like some corporate big brother, like kind of making sure that we can know exactly what our data scientists are doing. Why it is beneficial is that we expose a Python client that now allows the data scientists in their notebook to actually inspect the state of the workflow, so that even in real time, when the workflow is running, you can open a notebook and you can ask that, okay, so let's take a look at my latest run, and let me start like looking at the model that was just produced, or let me look at the scores, and let me look at which scores were working the best, and which models were working the best, and so forth. And now why this is important, this is obviously useful for troubleshooting, this is useful for monitoring, and so forth. But this is also useful because we ask ourselves this question that what kind of a UI, what kind of a user interface, graphical user interface should we provide for these machine learning pipelines? And now there are many solutions out there, and like many companies that even provide you dashboards and so forth, like that show the convergence of the model. And surprisingly, our data scientists said that, like, well, that's actually not the most important thing that we care about. Like, every single modeling pipeline had their own requirements, had their own KPIs that were relevant for them. So some of them, like, let's say, if it was something about like kind of different countries, they wanted to know like how's the different distribution per country, and like some other things maybe only wanted to know things about like a very specific variable in their pipeline or in their model. And now the question is that, like, well, it's very hard to have a single UI that would solve and address all these use cases. And then, of course, you can argue that, well, if you had a customizable UI and like you had something like Tableau where you can pull whatever fields and so forth, then yes, maybe you could. But then we realized that we already have that perfectly customizable UI. And what's the best part is that data scientists already know how to use it, and that's the notebook. The notebook can be the UI, so you can pull whatever information about the model, about the workflow you want, and then the data scientists can build exactly the types of visualizations and exactly the type of reports they want in a notebook. And then we have the mechanisms in place how you can then schedule these notebooks, so every time your model updates, your notebook updates, and there's a single report that every time shows what's the state of your workflow. And you can customize it like as much as you want. So it's very, very powerful. So let me show you actually how it works. So we already had like those tutorials, so let's look at another one. So we have the second one, which is a playlist. So if we open that one, it's like a bit more code, so you don't have to worry about the code too much. And it's just like a highlight few things. We have these nice features. You can include some files in your pipeline. You can add some parameters. But anyway, that's kind of a side note. The thing I want to highlight here is that we have this one step in our workflow that's called genre movies. And here we have this artifact called movies. And that basically shows the kind of the input to the model, like in this toy example. So now when we execute this pipeline, we can just run it here, and it executes locally. And now we can see that it actually like executed. Yeah, there is the playlist flow. So now what you can do is that like on your laptop, let's say, in this case, you can just open a Jupyter notebook, as usual. And in the Jupyter notebook, let's just do, I guess, like a standard Python 3. And then like you can import the Metaflow from the Metaflow package. And the Metaflow object allows you to inspect the state of the Metaflow universe. And here we see that, okay, there's our playlist flow that we just executed. So let's take a look at the playlist flow here. And now we can look at the latest execution, the latest run of the playlist flow. So that's the one that we just ran. And now we can start digging deeper, and we can see like what happened inside this run. We can see every single step that was executed. And in this case, we're interested in the genre movies, so let's take a look at the genre movie step. And now, thanks to the fact that these artifacts are persisted, we can start looking at every single data point that we have. So for instance, in this case, it was the movies that we were interested in. So let's take a look at the movies. And now here you can see that you can see the full data set that actually went to your model. And imagine that like this is your modeling pipeline and it had failed and you have no idea why the model didn't come out. And now you are able to go and like just check that, okay, let's check like every single variable. Let's just check the status. And naturally you can, thanks to the fact that things are persisted, you can also resume the computation locally that failed in production. So it's just really, really nice feature for debugging. Now let's switch gears a bit and let's talk about scalability. So Netflix obviously is a large company. We have, as I mentioned, we have hundreds of petabytes of data in our data warehouse. And now you might think that there is almost a bit of a kind of a paradox here that like we say that we allow people to write like really naive, idiomatic Python code, and somehow it's supposed to work in production. And now many of you who have ever used, let's say, pandas in a notebook, you may have experienced that you try to load like even a medium-sized data set in your notebook, and you load it in pandas, and then like, your kernel just dies because it runs out of memory. And like pandas takes way too much memory. There's like a lot of memory overhead there. And then like usually what happens is that you think that, well, anyway, you're doing it wrong. There are like, these big data infrastructure exists for a good reason. You should be doing it on Spark. Or maybe you should be, well, back in the day, people said that you should be using Hadoop. And yeah, I mean, that could work. But if you remember that full cycle there in the beginning and that jump like from going from your laptop to the cloud environment, and if we say that, well, yes, you have something that works in your notebook, now just rewrite it a bit so that it works with PySpark, it is a leap. And it is a new paradigm. And the operational behavior of Spark is quite different from local scripts. So it adds a lot of cognitive overhead. And going back to that idea of data scientist productivity, an interesting exercise here is to think that if the only thing that we cared about was data scientist productivity, what would be the optimal thing? If we don't have any other considerations besides how do we make data scientists productive? Well, you might say that, well, what if they could just execute the same code that they executed on their notebook? I mean, that naive thing with pandas, what if it just worked? Well, and of course, there's no magic and fairies that can make Python like scalable like automatically, but there's this one simple trick that we can do.Maybe we give them bigger laptops, and the bigger laptops exist in the cloud. So here, let's say in the step B, where the data scientists had their big data frame and it ran out of memory, maybe you can say that, well, I mean, in order to execute this function, I need 200 gigabytes of RAM. And now the largest typical not X instances on EC2 have a 768 gigabytes of RAM. And it's a pretty big data frame that you can fit in 700 gigabytes of RAM. And that allows the data scientists to keep their code as is. And now you might think that, yeah, well, that's super wasteful. But keep in mind that like these resources are only being used for the duration of that one function. And this is one of the big benefits of the cloud. And thanks to the elasticity of a backend like batch, we provide integration to AWS batch, which is basically a queue in front of ECS, the container management system. So that like when we execute this function, like batch takes care of scaling up the resources, it executes the function, maybe it only takes a few seconds, and then it scales down as needed. So actually it doesn't end up being so wasteful at all because we only need these resources for a relatively short duration of time. Another really interesting benefit with this is that imagine that like here in the step A, we are saying that our code requires 16 CPUs. Equally well, it could say that we require 8 GPUs. And now modern ML libraries like TensorFlow, like Keras, they are very well optimized for GPUs. And they actually perform mind-blowingly well on these large GPU instances. And actually the vertical scalability is quite preferable because you don't have to pay any overhead of network communication in those cases. So you can just say that, okay, so here's my data set and I need like 8 GPUs to execute this thing. And then on that one step, I run my TensorFlow model or I run my PyTorch model. And then it runs really, really fast because it's Python just on the surface and it's C++ all like below the surface. And it's a surprisingly nice model, like for these modern machine learning libraries. And now, not only you have these individual big boxes, another important thing that we have is that you can fan out. You can have arbitrary number of these quote-unquote laptops in the cloud. So like in this example, we define this toy parameter grid, X, Y, and Z. And in Metaflow, you can just say that, oh, I want to do a for each. I want to iterate over the grid here. And what happens is that Metaflow creates, in this case, 3 copies of this step A and executes A like with 3 different, with the different parameterizations 3 times. And all these things run in parallel. It's managed by batch. And this basically allows you to run thousands of containers in parallel. The largest workflows that we run at Netflix today using Metaflow run thousands of these containers in parallel. And you can imagine that like now that the only scalability limit is basically how much you trust that like EC2 can give you instances. And I can guarantee that it works pretty well. And of course, thanks to batch, you can also use spot instances. So the kind of the cost footprint is pretty nice as well. Funnily enough, one data scientist said that like it has been always easy enough to do the fan out. The fan in is the hard part. So here, like we wait for the results, and then like again, we collect all the results and let again the user to choose like which one they want to use. But now when it comes to scalability, the combination that you can scale up, and like you should really like take into account that the largest boxes that are now available on EC2 are like really like pretty big boxes, both when it comes to memory and GPUs. So you can do a lot with these boxes. And you can have many of them running in parallel. It gives you really a good amount of horsepower for these workflows. Now, of course, like what I'm not saying is that, that this would solve all problems. It's trivial to come up with the example like when this model fails. But the important thing to keep in mind here is that this works maybe for 80, maybe 90% of use cases that we have at Netflix. And for those use cases, this is incredibly productive and this is incredibly intuitive. This one nice thing is that when things fail, and of course they do fail, it's also like quite understandable what happened. It's not some like a mysterious shuffle, ran out of memory situation. But I mean like, well, box went away. Like we provide, of course, like retry everything, or maybe you just had like your resources too low. And typically these are like issues that data scientists can deal with by themselves. So there's no too much magic going on behind the scenes. Now the question is that how do you actually build these models? Well, I mentioned earlier that like we do dependency management as well. And this goes back to the question of the Docker containers. When you execute something, let's say with TensorFlow, obviously you need the TensorFlow, the library. And now the thing is that we could say that, well, you just need to have a Docker container that comes with TensorFlow. And well, then the problem is that, well, which version of TensorFlow? I mean, maybe one user wants 1.14, another user wants 2.0. Do we provide 2 different Docker images? Well, maybe, but I mean, you end up with this combinatorial explosion with all the frameworks that are available. You could say that, well, I mean, we only support these 3 frameworks, and then you are limiting the freedom of data scientists, and like, who likes that? But what we do instead is that we allow them to use any packages that are available in Conda. Conda is the package manager that also Amazon SageMaker uses. And we allow them to specify exactly the libraries they want. And now Metaflow takes care of creating these environments on the fly so that your code can execute with the dependencies that they need. So in this case, we can even have 2 different versions of the same library, which is really handy if you want to compare. If previously you were using TensorFlow 1.14, I want to see my model, how it looks like with that. I want to compare like if there are any adverse effects if I upgrade to 2.0, and you can run them in parallel. And now notice here that the user doesn't have to bake any Docker images. So we take care of like instantiating these environments on the fly. And what's really, really, really important is that when you deploy these workflows in production, and like what the feature that we also have is that you can export these DAGs to a kind of a production-grade workflow scheduler, like maybe step functions, which is something that we are working on. Then we freeze the full manifest of all dependencies, including the transitive dependencies, which guarantees that even if one of these libraries changes upstream, your workflow won't break. And this is I don't know if many of you or any of you have seen this issue, but it caused quite a bit of headache to us that data scientists use all kind of libraries. And some of these libraries are developed by people in academia who really don't care so much about stability, and suddenly the library upgrades and it breaks the production pipeline, and that's not fun. And that's why we decided that we want to freeze the full environment so that this can't happen. In some cases, it might be that you don't care about thinking about libraries at all. Maybe you just want to get results as easily as possible. And for those cases, we have integration with SageMaker. So for the past couple of months, we have been working with the AWS SageMaker team to provide a really seamless integration between SageMaker and Metaflow. And of course, now SageMaker already comes with a very high-level, highly productive API for data scientists. But one nice integration that we have done here is that typically when you use SageMaker, you or the data scientist has to manage, let's say, the S3 location where the data goes. So you have to say that my data lives here and my model goes here, and then you have to load and store data again. When you are using SageMaker in Metaflow, you can just say that, well, here's my data set, it's this artifact. And given the fact that Metaflow already stores everything in S3, we can just fetch the artifact, give it to SageMaker, let SageMaker run with the data set, and then we grab the result, which is then stored as a Metaflow artifact. So it is fully versioned and persisted in S3. And available through the client API in a notebook if you want to inspect the results. So this is not just talk. Let me show you how it works in practice. So here I wanted to show that this is actually now configured to use AWS. So we have the metadata service running in the cloud. And let's just hack this HelloFlow example that we had before so that it actually runs code in the cloud. All we have to do is that let's say in this case, we want to define this a toy hyperparameter search. So let's define 8 parameters. And let's say that we want to do for each over these parameters. That's all we have to do to get the fan out. And then let's say that here's the hello step, and maybe it could run a big model. So we need 8 CPU cores, we need 10 gigabytes of RAM. And we will run a separate instance of this step for every input parameter. So we get 8 instances of this one. And let's just store the parameter in X just to make it simple in the interest of time. And then we need the fan in step where we collect the results. So we get all those 8 inputs, and just to show that it works, let's just sum over the inputs. So whatever is 1 plus 2, and 3 and 4 and 5, 6, 7, 8. And let's print out the result here. And then we complete the workflow. So that's all we have to do to say that here's the one compute-intensive function, hello, that we want to execute, and we want to execute that in the cloud. But everything else still runs locally. So you get the best of the both worlds. So this runs in the cloud, and then everything else here, even the join step, runs locally. So you get the rapid prototyping of your local machine, and you get the infinite capacity of the cloud. So let's run it and see what happens. So now when we execute the code, in this case, since we are using the cloud, we register with the centralized metadata service, and now this start step runs locally on this machine. It says that, okay, now we are yielding 8 steps, and now it's starting to launch these child steps. And now we actually print out the batch ID. It's really nice. If something fails, you can go to the batch UI in the AWS console and see what's going on. So we don't want to hide the fact that it's running in the cloud. But now all these containers are running in parallel. And if the cluster hadn't been pre-warmed, AWS batch would take care of scaling up the cluster so that you have enough resources to run 8 things in parallel. And now we have all these 8 tasks executed, and now we are starting to run the join step. The join step says that, okay, the result is 36, and that's our workflow. And now you can imagine that what this means for a data scientist. You are just writing idiomatic Python code. You are using your favorite machine learning libraries. You can combine the batch decorator and conda decorator, and we will take care of instantiating, let's say, TensorFlow on batch. And you can just run it locally. You can keep hacking. And then remembering that part where you are moving to the cloud. This is all you have to do to move to the cloud. It's just one line of code. That's all you have to do. And thanks to the fact that you can use these big boxes, I mean, the scalability story is pretty solid as well. Now, these are the main features that we have in Metaflow. And if you remember the stack that I painted in the beginning, We had the data warehouse. Now we are storing everything in S3. We have the compute with AWS Batch. We have the orchestration with the local orchestrator, as well as the upcoming integration to step functions. Then we had the question about how do we define these workloads in the first place? How do you define the architecture? Now we have the DAX structure that's very understandable to users. It's very simple, idiomatic Python code. And there's the question, how do we version everything? We persist everything in S3, the code, the data, the dependencies. And then there's the question, how do we operate everything? We provide the notebook integration for operations, so you can the data scientist can monitor and inspect the state of these pipelines by themselves in their own notebooks. And then finally, we allow the user to use their favorite libraries thanks to the Conda decorator, so they can use TensorFlow, XGBoost, whatever is available in Conda at the top of the stack, so they can do whatever they want at the top of the stack. And this whole package now, which looks very simple, as it should, it allows them to own the end-to-end pipeline. And one thing that we are working on, you might notice that there's the deployment part missing, so we have a system for that internally. We are evaluating whether there's appetite to have something like that available, or maybe you want to use SageMaker deployments, so we're working on that integration. But basically, we have the full cycle now closed, and we have all those parts. Now, when we started about thinking to open source Metaflow, the small realization that we had is that for many individual data scientists in organizations that might not be already using AWS, or maybe their AWS account is managed by someone else, it might be pretty hard to give this a try, because you have to install, factually, you have to configure S3, you have to configure Batch, you have to configure this metadata service, you have to do these things. And as all of you as AWS users know, it's doable, but takes some effort. And we started thinking that, well, would there be a way how we could make all this easier? Again, putting that data scientist productivity hat on, can we even make the onboarding to Metaflow easier? Since if one of you wants to give it a try, but you are not ready to install and make all these changes on your AWS account, how we could actually do it? And we started working with the AWS Service Catalog team. And if you are not familiar with Service Catalog is this extremely nice product provided by Amazon that allows you to define full, almost like a mini accounts inside AWS that define a full stack, all the components that you need to execute a certain product or a certain workflows. So we work with Service Catalog to make it possible to provision these Metaflow sandboxes, isolated execution environments in our account, so that you can just start trying Metaflow. You can actually go to the Metaflow documentation right away. I recommend that you go to the documentation, you look for a Metaflow sandbox, you read what it's all about, and then you can go to this address, metaflow.org/sandbox, and you can actually sign up for your personal Metaflow sandbox. That's an isolated Metaflow test environment that is provisioned and managed by Service Catalog behind the scenes. For those of you who are interested in more technical details, how it works is that we have one big CloudFormation template, and this CloudFormation template is available as open source as well. That basically sets up all these individual components. So it sets up AWS Batch with managed compute backend. It sets up a SageMaker instance. It sets up a custom S3 bucket. It sets up metadata service with the Postgres backend. It sets up everything. What's a really interesting feature about this is that obviously we are really concerned about security, wanting to make sure that no one can abuse the system. And hence this sandbox environment doesn't have any internet access. And now, interestingly, when you think about these machine learning workflows, why do machine learning workflows overall need internet access? So typically it's that data goes in and you do some processing, you do some training, and then data comes out. So you shouldn't need internet anyways. Well, one reason why you do need internet typically is that you need to install these external packages. But thanks to the Conda decorator that we provide, we can create those environments even in these secure, no internet environments, so that you have this a fully featured data science environment that is fully isolated from the outside world. And for those of you who work in more regulated environments where having the control about the data that goes in and the data comes out and the guarantees that nothing ever leaks out, this is something that you should check out. Just to make sure that you believe what I'm saying, let me just show how it works. So this is the sandbox sign-up page. You can go there today. And please take note that this is only meant for test and evaluation. This is not for production. When you agree to using the sandbox, you have to sign up with your GitHub account. We just want to make sure that you are not the bot. You are taken to this page. Typically, it takes a while before you get your sandbox. We have limited availability. And now, eventually, you will get a configuration string that you can just copy to your clipboard. You click there. And then you can go to your terminal and you just write Metaflow configure sandbox. And you just copy-paste that long string there that basically includes all AWS configuration. And now you have a fully functional data science environment in the cloud. It uses now your personal metadata service. In the real production setting, you probably would share it with more people, but this is for evaluation. So let me just quickly demo it for you. So now let's just open our hello world example again. And just to show how we operate inside Netflix, let's say that we have some artifact here, a model. Let's say that we are training a model and we get some model artifacts. So just demo how it works. So let's print it out. It's called model. And now, the thing I want to demo here is that if we execute this locally, we are not actually executing this in the batch. You actually get with your own batch cluster as well. But I mean, let's execute it locally. So this runs on your laptop. This runs on my laptop here. That's my username. Now it gets actually a new ID from the centralized metadata service. It runs the code. And here's the artifact. But now the nifty thing that I want to show you is that when you go back to our page here, there's actually a link to your personal SageMaker instance. You can click the link, and it takes you to the SageMaker notebook. That's your personal notebook that's attached to the metadata service. You can open a notebook here. Let's do a Python 3 notebook. And we have the Metaflow package pre-installed for you, so you can, again, just import Metaflow. And I just want to show you that it's actually using the centralized metadata. So let me write here, sorry, it should be metadata. And we need to switch the namespace. So let me just show that it's using actually this cloud-based service. That's the cryptic address. You don't have to care about it. I just wanted to show it to you. And now the notebook doesn't know who I am, so I'm just telling that I'm interested in everything happening in my own personal namespace. And now we can start asking the questions that, okay, so what kind of workflows I have run in the past? And when I list all the workflows, I see that, okay, there's the hello flow that I just ran. It might be still running. I mean, I guess it was running when we switched the window. And let's take that flow. And now let's look at the latest run. I think it was the run number 3 that we saw there. Yes, there's the run number 3. And now again, as I showed you before, now you can start inspecting the internals of the workflow and the internal state, thanks to the fact that we persist the artifacts. And there's the model that we added. So let's do the model, and now it prints out the model. And now, of course, in this case, it's just a silly dictionary. It doesn't seem like much. But you can imagine that now this could be an actual model that you trained. And what this means, and this corresponds to the actual setup that we have at Netflix. At Netflix, we persist everything in these workflows in the cloud, in S3. And we have a centralized metadata that records absolutely everything that gets run in Metaflow. And now anyone can open a notebook and start asking the questions well, I mean, for a certain user, for myself, what are the latest executions, and can I get the latest model? And can I see what was the data going in, and things like that. And the interesting thing here, as you can see, that this happens in the SageMaker notebook. It's a cloud-based notebook. You can run it with an instance of any size, and you can still access even the stuff that people run locally. And that's kind of the perfect marriage between the local machines and the cloud. It works exactly the same way, regardless whether you run it on your laptop or whether you run it on AWS batch. So that's pretty much Metaflow. And now I just want to conclude my talk by saying that we have been using Metaflow in production at Netflix for the past couple of years. Now we have over 600 projects running on Metaflow at different levels of maturity. So by definition, not all of these projects are super business critical, but we want to support data scientists all the way from the prototype to production. And Metaflow makes it easy enough that you can use it as the first tool when you start prototyping something. You will use it in conjunction with notebooks. You get the best of the both worlds again. And then when you are ready to start scaling up, you can leverage the AWS features to get any scale you need. And then we provide the features like dependency management, like audit trails, like versioning, like tracking that you need to build these robust production pipelines. As I mentioned, Metaflow is open source at metaflow.org. Go and take a look. And I will be at the Netflix booth after this presentation. So if you have any questions, you can come at the booth, or you can reach out to us by email, and you can find the contact information at the site. Thank you.